So, hello everyone, welcome back for our second talk. And today we have Doosung Park from the University of Zurich, who will talk us about logarithmic motifs over a field.
Thank you for inviting me as a speaker.
Sorry, could you increase your microphone?
So don't you hear me?
Yes, now I hear you.
Okay, sorry. Thank you for inviting me as a speaker in this nice conference. So I will talk about logarithmic motifs over a field. This is joint with Federico Binda and Corana Usber. So motivation is this. There are lots of non-A1-invariant cohomology theories. First, we can consider Hodge cohomology. Here X is a scheme over a field like this, and this is an invariant. Or we can consider omega x over z q. That's also not A1 invariant. And we may consider non-connective K theory, Bas K theory, or this is motivic homology. This is unconstructed. So, I can say some expected expectations. So, a current motivic homology due to Voevodsky is A1 invariant, and we may want something non-A1 invariant satisfying these conditions. So yes. Okay. Expectation is H motivic homology of x comma z is H is Navier homology of x comma z, and H motivic homology of say P x comma z1. So we can say this is just P, and P is any integer. Is also H is Navier homology of P x comma gm. And this is not A1 invariant because, for example, if P is 1, P minus 1. P is 2, then this becomes Picard group of X, which is not A1 invariant. If X is not, in general, if X is not a normal string, they are not isomorphic. And also, we also expect that this is ZPP is linear K theory linear K-theory of X if X is spec A and A is local. Okay, so we may want some motif cohomology satisfying these conditions. So the problem is to construct such a cohomology theory. So probably.
Sorry, can I ask a question?
Yes.
Is the cohomology supposed to, I mean, do you want it because it's supposed to fit in a spectral sequence converging to K-theory?
Yes, yes, that should be also one good property.
Okay.
Like Atiyah Hilbert spectral sequence. Is it okay?
Yes, thank you.
Okay.
So your X is not smooth, right?
X is general. If X is smooth, then this is already constructed by Voevodsky.
Okay.
So X is not smooth. X is general, just scheme. Say over K, field K. Or general over Z, but anyway. So I will given some nice computation. So if X is spec K, X over X to the 1, and K has characteristic 0 field, then this is due to Jinhyun Park. Jinhyun Park and Bloomberg. Milner K theory of X is isomorphic to Milner K theory of K, and sum with a direct sum of i's from 1 to m omega K over Z n minus 1. So somehow Milner K theory is related to Hodge drum differentials. So differentials, Taylor differentials. Okay. So even though the value realization of A1 is a C, which is contractible. A1 is not contractible in algebraic geometry. Because there are lots of cohomology theories which is not A1-invariant. So I will explain some fundamental reason why A1 is not contractible. So reason is that in algebraic geometry,
there is a question in the chat.
yes.
Oh, I think it's referred to the formula for Milner K theory above is n minus 1 is I minus 1.
No, n minus 1.
N minus 1. Okay, so it's just n copies of the same group there.
Right.
Thank you.
So there algebraic geometry and algebraic topology. So here algebraic topology, as far as I can imagine, there are no non-reduced topological spaces. But here we have something like K x over x to the n plus 1. So they are reduced schemes. And if some cohomology has philosophically origin in algebraic topology, then that may not capture the non-reduced parts. So for example, entire cohomology or arithmetic cohomology. So there is a comparison between arithmetic cohomology and singular cohomology, basic cohomology if the characteristic is 0. But so we may say that arithmetic cohomology has a origin in algebraic topology philosophically. So in this case, entire cohomology does not see the non-reduced part. But usually cohomologies are has origin in algebraic geometry. So suppose A1 is contractible. Suppose A1 is contractible. Then this implies that we have localization property. So I is a closed emergent, and J is open complement. Then there is a distinguished triangle. Like this. So this, at least for SH, this is true. So A1 is contractible means this localization property. And we can deduce that this one is then spec. So stable homotopy category of spec X is equivalent to stable homotopy category of spec X reduced. So we cannot distinguish the non-reduced cohomology and reduced cohomology. So non-cohomology for X red, reduced and cohomology for X. So A1 localization destroys this structure. So we should not invert A1 to figure out what's going on for X non-reduced. So I will just explain some picture of good cohomology theories. So SH, so S is a scheme. So stable homotopy category of schemes. So category of P1 spectrum, and localized at A1. So A1 localization and P1 stabilization. So these are two ingredients, and another ingredient is sheaves with mismatched sheaves over smooth over S. So with these three ingredients, we obtain stable homotopy category of S. On the other hand, we can consider just sheaves, mismatched, and say just S1 stabilization. So then we obtain homotopy category of S1 spectrum of mismatched sheaves like this. And Okay, so we have this free-faithful functor. And Voevodsky proved that K lives here. And also a theorem due to Voevodsky and Sisinsky is KH lives here. So K cannot be in SHS because K is not A1-invariant, but somehow we can expect that there is a diagram SH good S. And SH good of S should contain K. And KH also because they should contain SH as a full subcategory. So in other words, SH good of S contains or should contain all good cohomology theories, including K-theory, motivic cohomology, Hodge cohomology, and probably algebraic cobordism. Moreover, we should expect that SH good S is a triangulated subcategory. Of homotopic category of S1's spectrum. So homotopic category. And moreover, we have some behind the structure, like model structure or some infinity category structure, such that the homotopic category is SH good of S.
So, sorry, can I ask you something, because this condition 2 seems very weird to me. Because, for example, SH is not a triangulated subcategory of sheaves of spectra, because the transfers, so to speak, the deloopings are additional information.
Really? Okay. Probably this is wrong. Okay.
I want a forgetful functor. That much is clear.
Okay, but okay. Sorry. So as a triangulated structure, okay, sorry. So triangulated category. Okay, so at this moment, it is not clear how to obtain SH good of S if we begin with smooth schemes over S. So somehow, so the idea is to extend this category and to change A1. So we need to use another one. So the idea is smooth log smooth over S, which is the category of pairs X, D, where X is smooth or log smooth over S, and these are strict normal crossing divisor. such that these also the user parts are smooth over S. Say that's a strict normal crossing divisor. Okay, and morphisms requires some additional data. So morphism is like this: y comma e to x comma d. So that should be like e to d y x. But so because d and e are strict normal crossing divisors, d is locally induced by some monoid structure. Say monoid structure, say locally, in n to s. So there is some. So each n corresponds to one divisor, and if there is an r irreducible divisors crossing, then there is a map from nr to gamma of d comma od locally, and we require that this map is induced by some monoid homomorphism. So locally, precisely locally. So that's the category, and the compositions are obvious. So that's the category of smooth log smooth over S. And also we can consider some general category like log smooth over S. So X has only toric singularities, and D can be also some more general or little more general so this stands for log smooth. So I will not explain the definition.
So there's a question about whether the square you draw there needs to be Cartesian.
No, not Cartesian. So Cartesian, if that's Cartesian, then that's called a strict morphism. But usually we don't require that the square is Cartesian. And okay, and we need a topology. So because mismatch topology plays a crucial role in stable homotopy theory. So strict mismatch topology. So y comma e to x comma d is a strict mismatch cover if y to x is a mismatch cover. Okay. And the diagram is Cartesian. So E is the same as y times xt. Okay. And so we get sheaves with strict mismatch of smooth log smooth over S, or sheaves with strict mismatch log smooth over S. Okay, and on the other hand, so we can define some. There is a notion of log étale morphisms. Generalizing étale morphisms. So y comma e to x comma d is a dividing cover if it is surjective, so surjective means y2x is surjective. Surjective proper logoethal monomorphism. Proper means y2x is proper. And monomorphism is in the category. So also we can define sheaves with dividing plus DNS is a shorthand for dividing plus strictly average with smooth, low smooth over S. So these are new topologies, and A1 is replaced by P1 comma infinity. So this is a proper scheme over K or over S, so P1 times S. But so A1 S is replaced by this. This is proper over S. Okay, so as a result, and also AN is replaced by Pn minus 1. So Pn minus 1 is an infinity divisor at infinity. So hyperplane. And we say this is this one. And informally called box or cube. Okay, so we have like sheaves. So I'll explain this to them. So sheaves with strict mismatch and smooth low smooth over S, and invert or Pn minus 1 okay, and so P1 stabilization. So these three. So if we take these things, then that's equivalent to sheaves with dividing mismatch. Dividing mismatch topology, but smooth, low smooth over S, and invert just the box, and P1 stabilization. And there is another thing which I will explain. So admissible blow-up is a morphism y comma e to x comma d such that y minus e to x minus d is an isomorphism. So, and this is the class of admissible blow-ups. And then there is another equivalence, sheaves with dividing strictly sandwich. Low smooth over S, and invert box, and invert.
Sorry. There is a question about what you mean by inverting box. Do you mean
box localization?
You mean multiplicatively invert, or to make it like in A1 in classical homotopy theory, saying that?
Right. So replace A1 by box. So invert. So I will write a more clear statement. So invert point to box.
Okay.
So the same in A1 theory, we invert this one, point to A1. But box is a compactification of A1, so say this is I0 or I1. Or general or box to just point. They are the same, but
Okay. Thank you.
and also P1 stabilization here. So these three constructions produce an equivalent category, that's theorem. So the construction is denoted by log sh of s. Sorry, no. So they are equivalent. So if s is k is a field, and we assume resolution of singularities. So this is only work for S is when K. So we get log SH. And the next question is to figure out whether this log SH is the construction for SH good or not. So I will explain some functors. So we have smooth log, smooth over S, and smooth over S. There are three functors, eta, lambda, and omega. So eta is left adjoint to lambda, lambda is left adjoint to omega, where eta of x comma d is just x, lambda x comma d, x is just, so x lives in smooth log, smooth over S, or smooth over S, x comma empty set, and omega x comma d is x minus d. So using these three functors, actually we can just use lambda and omega, but it is helpful. So we obtain a stable homotopy category S to log stable homotopy category omega upper star to stable homotopy category of S on spectrum. And this is lambda upper star. So F just maps to, but, and say R, but I will mean R, but, and so the derived functor of this one, and F, so and derive this. F maps to F lambda, and derive also this. So we have these functors, and our question, I will not say this is a conjecture because probably it is early to say this is a conjecture. Question is, R omega upper star and R lambda upper star are fully faithful.
What? Sorry to harp on this again, but what exactly do you mean with S1 spectra over S? I thought you meant sheaves of spectra over smooth S.
Yes, smooth.
But then the composition is not fully faithful, so. Right, because you have a map from KGL to little KGL, sorry, from little KGL to KGL, the very effective cover. That's an isomorphism on, I think it's an isomorphism on S1 spectra, or maybe it's not. No, yeah, it's an isomorphism on S1 spectra.
Okay, so are you saying that this is not true?
I'm saying that, I believe that R omega upper star is fully faithful. That would be my natural conjecture. But it says they cannot both be fully faithful unless I'm completely mistaken.
Okay, so probably this is my my stupidity. Okay, so
as far as I understand, what Dennis is saying is that the composition. So we don't. Your audience, at least us, we don't know much about this log guy in the middle. So we are learning from you. But the composition is probably is it like the usual GM loop space functor, infinite GM loop space, or no? Because that guy, the composition, if it's the same as infinite GM loop space, then as far as I understand, it's not fully faithful. And I think that's what Dennis is saying.
Yes, okay. Okay. Okay, sorry, but
he didn't invert A1 in the right hand side.
What if this is P1 instead of S1? Is it also wrong?
Okay, with P1 I could believe, but then I would, if you don't ask for A1 invariance, I would have to, I would believe it much more, but I'm a bit uncomfortable. Okay.
What is the difference between SH of S and SPT P1 of S?
There is no A1 invariance on the right hand side.
No A1 invariance.
The right hand side is not the triangular category.
Okay, so okay, but anyway, so sorry, so forget about this. I'm not confident with this. So anyway, this is really reasonable. R omega upper side is fully faithful. Sorry about that. So I will continue. Log motifs. So if we can say that R omega upper side is fully faithful, then log SH of S is an extension of SH of S. Okay, so definition. So log correspondence. So here X and D and Y and E are over K, where K is a field, and suppose X and Y are integral for simplicity. Then L core of Y comma D, X comma Y comma E, X comma D is a set of Z and set of this formulation. So Z X times Y and Y X. This is the same as Voevodsky's definition, finite surjective. and this is closed immersion. But we care about the boundary structure. So take the normalization. And consider this map, composition and composition. And say this is P and Q. And then we require that. So this data plus the data of Zn, and consider Zn times XD. So Zn is not smooth, but we can still, so this is not in log smooth over S, Sk, but we can still define this one as a log scheme. And we require, another data is this morphism of log schemes. X, D and Y, E. So we require this and take Z. Okay, so this is log correspondence. So Z is also irreducible here. So this is a generalization of log correspondences. And then we obtain log transfers of X, D sheaf as in Voevodsky's theory. And we also obtain sheaves with log transfers over K also. And we consider strictly Nissenevich topology or sheaves with log transfers dividing Nissenevich topology. And we can use the same construction before. There were 3 constructions, and we can do the same thing. So for example, so log smooth over K and sheaves strictly Nissenevich log transfer log smooth over K and log smooth over K. And then we can do the same construction to obtain log Dm. Effective K. So if we stabilize P1, then we may get log Dm, but because we don't know anything about cohomology in log Dm, so we did not write anything about that because we don't know the cancellation theorem. Anyway, we can obtain log Dm. So we invert. So sheaves with strictly Nissenevich log transfers, smooth over K, and invert R box, invert R Pn minus 1 for our n, and sheaves with dividing Nissenevich sheaves log transfers, log smooth over K, and invert box, and also sheaves with log transfers, strictly Nissenevich sheaves, log smooth over K, and invert box plus admissible blow-ups. So these 3 things also produce log Dm. Okay, so the theorem, one of the main theorems in our paper is this. So we can define omega per star, R omega per star, say, from log from Dm effective K to log Dm effective K is fully faithful. So, assuming resolution of singularities. Okay. So in the remaining time, I will explain some ideas of the proof. So, so if F is a sheaf, then we can consider Sing F, Sing A1F. So recall that this is something simplicious, which is obtained by F A squared F A1 F point like this, and A1 is given by point is point, A1 is A1, but A2 is given by this 0, 0, 1, 1, 0, 1, and these three maps are given by these three lines in A2. That's A2. And like that, there is a well-known construction of Sing A1. And we can compactify A1 to box. So we can define naive Sing. The same one, just compactify everything. But the problem is that this is not so useful. So for example, F to Sing, naive Sing box is not box weak equivalence. So we can introduce box local model structure like A1 model local model structure, and we can discuss about box weak equivalences as A1 weak equivalences. But I don't have any formal proof, but this, I believe that this is not box weak equivalence. So Sing box is not useful to obtain any kind of so naive Sing box is not useful to obtain any kind of finite resolution. So the idea is this. This is because box is not an interval object. The meaning is we have a multiplication map such that so P is from box to a point, and I0 and I1 are the two 0 point and 1 point. And we require that M identity times I0 is M identity, I0 identity R I0P, and M identity times I1, M composition I1 times identity is this identity. So we require this to say that box is an interval object, but this is wrong. There is no such a morphism M. And this is the reason why we cannot, we say that this is bad. Okay, so the idea to remedy this one is we invert admissal blow-ups in the category. So we begin with low smooth over K, but we can invert all admissal blow-ups in this category. So, so I will say that admissible class of admissible morphisms admits factors of right fractions. Assuming resolution of similarities. And we can define some adjunctions actually, and we can define presheaf, smooth, low smooth over K presheaf like this. Say this is V lower sharp and V upper star. And V lower sharp is left adjoint to V upper star. And the true thing of this one is given by V upper star naive thing box F and V lower star, V lower sharp. So thing is a simplicial complex, simplicial sheaves, but we can also define V lower sharp and V upper star for simplicial presheaves. And also we can define this one for sheaf version. Okay, and then we can show that F to thin box F is a box plus admissal blow-up class of weak equivalences. Okay, we need admissal blow-ups here, not just box weak equivalence. But in the above theorem, so these three are all equivalent. So if we just consider this one, then we automatically get admissal one. So in log DM, admissal is automatically inverted. So this means that is an isomorphism in log DM effective. So this is a thin functor we use in the proof. Okay. So the idea of the proof is this. We need to compute cohm in log DM M Y M MX is here Dini's sheafification and Z log transfer of X. And suppose X is just a scheme, some smooth over K, but we also assume that X is proper. So this is the main computation toward the proof. And Y comma D is just low smooth. But Dini's star of Z log transfer of X, that's isomorphic to omega upper star of Z transfer. This requires that X is proper. And this is a lemma, crucial lemma, using some platification. And And then this is thing, so C star box of omega upper star Z transfer. So here, C star box is abelian version of thing box. And that's, so this is what we have covered. And then this is, this part is easy. We can interchange omega star and C star A1 X. And this is, or as we already know, this is A1 local. And so it remains to check that, so is F A1 local, then omega per star F is A1 local. So that's the remaining question. So that, sorry, this is box local. So that, so log dm home, log dm my comma d comma a Denise z for of x becomes home log dm effective my comma d comma omega upper star c upper star a1 z transfer x. And then, so if this is box local, then actually you can compute this one as a shift cohomology, hypercohomology of y minus d. So because we have w omega here, like this. So probably I need to add some shift here, but in this case this is 0, and some, if we have some shift, then this is negative n. So we have this hypercohomology like this. So
Did we lose the speaker?
Looks like that. I can pause the recording actually.
start.
Okay, you can go.
So, lemma is omega upper star f is box local if f is A1 local. And so H of strictness names top cohomology of x comma d with omega upper star f is isomorphic to this one. We need to achieve this. And to achieve this, we need to generalize Voevodsky's result, which is J is from x minus d to x. Say the open immersion, then Nisnevich cohomology. Hypercohomology of this one is Nisnevich cohomology of just like this. So in Voevodsky's result, this is just a smooth divisor. And I guess f is just a sheaf. But we need to generalize this one to normal crossing device, strict normal crossing divisors, and f is a complex of sheaves. So with these two ingredients, we can deduce that omega upper star, R omega upper star is fully faithful. So that's all I want to say today. Thank you.
Okay. Okay, thank you very much for your talk. Are there any questions?
I have two questions, but maybe I'll only ask one of them. Classically, you get a lot of mileage out of the Dold-Thom theorem in terms of constructing Eilenberg-MacLane spaces, if you like. So I guess one question, I remember talking to, I think, Marcus Spitzvik about approaches to the motivic Steenrod algebra using the symmetric power functor on varieties, but a problem with that is that these things are non-smooth. If I recall correctly, which is probably not right, because of things like the diagonal and the fat diagonal. But now you have these log structures around where you can try and isolate such things. Does this help? Have you considered the Dold-Thom theorem or the symmetric power functor on and how it behaves on this category of log motives?
Right, so that's a very good approach. Yes, but I'm not sure. So that should be useful for constructing transfer structures in characteristic 0. But actually, isolating non-smooth part of symmetric powers, is it known? It should be very helpful, but I'm not sure. If we know how to deal with the non-smooth part with the log structure, but I don't know.
Thanks.
Okay. Other questions?
Could you show, please, again, in the very beginning, the formula about Milnor-Key theory of truncated polynomials?
Okay.
Thanks. Thanks. Good.
Okay.
No.
Questions? Doesn't.
I will ask my second question then.
Okay, go ahead.
Are there, suppose you take, you look at these log motives and you rationalize them. Are there any kind of exotic power operations that show up here that sort of aren't coming from the classical motivic Steenrod algebra? So for example,
Sorry, I made a mistake. 1 second. Sean, sorry, I muted you by mistake.
it's okay, Dennis. I won't take it too personally. So Mike Hill found some exotic Dyer-Lashoff operations and rational equivariant theory, and maybe there's something similar in this log setting, just even degree 0 operations.
Right, and we have not thought about that too much.
Thanks.
But my expectation should be there is some similar one in log setting.
Thank you.
Okay. Are there any other questions? So if not, let's thank the speaker again. And we will meet in 2 hours at 4:30 European time from Tariq Sayed and Akhil Mati.
Yeah, and the room is open if someone wants to chat.
Yeah, that.
You're welcome.
If you. Oh, let me stop the recording.